Hey guys, this is Mike from Arnold Tutoring. Thanks so much for coming to the exam prep seminar for Math 1500 on the weekend. I hope you really found it helpful. And we have so much more content available on our YouTube channel here as well as our app 18 Now. So I hope you check all of that out and I hope you crush your exam and any other math course that you're taking. I wanted to go through in video format the practice exam solution key so that you can see not only how the solutions are done on paper, but how I would actually talk through them and think through them on exam day. First things first, there was a small error in the function that we wanted to use for question 1. So I've rewritten it here, what we want to use. You can ignore the one on the practice exam. Apologies for that. You can still work through that one, but it won't work as well. And actually one of the derivatives has an error. So I would focus on this one because it'll look a little bit better as far as curve sketching and would be more indicative of what you might see on the exam. So here we go. Let's go through that checklist. The first thing is domain. So that is part A. I'm going to try and do the video, or at least half of the exam in one video and then maybe the second half in another. I don't want them to get too long, but I also want them all sort of in one place for you. So the domain, the only rule we really have to look out for in a rational function like this is x values that will make the denominator 0. Since x squared plus 6 can never be 0, and you can test that by setting it to 0, and then x squared would have to equal negative 6, which obviously something squared cannot. So there's no restrictions, so the domain is just x as an element of the reals. Or if you want to write it as negative infinity to infinity. For symmetry, how do we test for even or odd functions? We just plug in negative x everywhere we see an x into the function. So it's going to be negative x squared minus 3 over negative x squared plus 6. And we know when we simplify this, negative x squared is just x squared. So it's x squared minus 3 over x squared plus 6. This is equal to f of x, the original function. And when f of negative x equals f of x, that is an even function. So it will be symmetric over the y-axis. So something to think about as we get closer to graphing it. Oh, that actually wasn't part B. It was just the second bit of part A. Then equations of vertical asymptotes. Since there's no values that make the denominator 0, there are no vertical asymptotes. What about horizontal asymptotes? We look at the degree of the numerator and the denominator in f of x. Since the degree is 2, because there's an x squared on top and an x squared on the bottom, all we have to do is take the limit as x goes to infinity and just divide everything by that highest power in the denominator. We know what this is going to come out as, though. This will give us 1 minus 3 over x squared over 1 plus 6 over x squared. Still doing the limit as x goes to infinity. And that just equals 1. Again, we knew that from the beginning because those were the coefficients in front of the highest term in the denominator and the numerator. It was like 1 over 1, which equals 1. So that means at y equals 1, there will be a horizontal asymptote. I like to sort of highlight each important aspect that we calculate throughout so that we know, what points go on the graph and what points do not. Okay. Next up is, so we've got our asymptotes. Next up are the critical numbers of f of x. Critical numbers are where the first derivative is either 0 or undefined. The first derivative is given to us. It's 18x over x squared plus 6 all squared. Once again, there's nowhere this is undefined because the bottom can never be 0. But the top can be 0 where 18x equals 0, and so that happens at x equals 0. So that is a critical number. We can also sub that in to find the actual point because that's going to go on our graph. F of 0, just plug that into the original, you get negative 3 over 6, which is negative 1/2. So the point 0, negative 1/2 will be a critical point on our graph. Intervals where f of x is increasing versus decreasing. I'm going to do this all together. The way I do it is I put 0 on the number line. I figure out if f prime of x is positive or negative to the left of that. So all you do is plug it into the first derivative here. When you plug in a negative number, first of all, one thing to notice is because of this squared on the bottom is always positive, so you don't even need to worry about that. The top is 18x, so when you plug in a negative number or something less than 0, you're going to get negative, which means that the function f of x is decreasing to that point. And when you plug in something positive, you'll get a positive over a positive, which means f of x is increasing. So we test around the critical numbers in the first derivative to see what we get for the signs of the first derivative, which match up to the direction of f of x. This is clearly going to be a local minimum because we're going from decreasing to increasing. So the intervals of increasing, just to write it out, are from 0 with a round bracket to infinity, and the intervals of decreasing are from negative infinity to 0 with a round bracket. Once again, we use a round bracket because at 0 we know the first derivative is 0, meaning the function is flat. Local minimum or maximum values, so now we know that we can say this is a local minimum at 0, which we've already found the point. Make sure you plug it back in to find the values, in other words, the y-coordinates. No local maxes to worry about. Now intervals where f of x is concave up. I'm going to try and do this on the same page because I think it's so important to show how similar this is to what we just did with the first derivative. Concavity is done with the second derivative. So I'm again going to look at my second derivative and set it equal to 0. 0 equals negative 54 into x squared minus 2 over x squared plus 6 cubed. Once again, the bottom, something squared plus 6 can never be 0, so we don't need to worry about that. It can also never be negative, so we don't need to worry about that. I'm going to multiply it up to the other side, and we can just set the top to 0. This will be 0 when x equals plus or minus root 2. Don't forget the plus or minus. That's what will make the bracket 0. So I'm going to put those values on here, negative root 2 and positive root 2. I'm going to put little zeros above because that's what the second derivative is at those points. And now I'm just going to test numbers outside. And again, I'm testing into the second derivative here. Bottom is always positive, so I can ignore that. The top will be negative on the outsides because we have a big negative 54 times a positive. Same thing out here. But in the middle, if we sub in 0, we'll get a negative times a negative on the top, which is a positive. So we're going concave down to concave up to concave down. Great, so we know that at root 2 and negative root 2, those are points of inflection. So the x and y coordinates of the inflection points are, so I'll say P, O, I, points of inflection, negative root 2, and if I plug that in to my original, I get 2 minus 3 over 2 plus 6, which is negative 1/8, or positive root 2 and negative 1/8 as well. We know these are going to be the same because we know our function is even. So that's really all we need to do. You find those spots where the first derivative equals 0 and the second derivative equals 0 and do the same number line test around them to determine increasing and decreasing with the first derivative and concavity with the second derivative. Now let's plot this all and then we're all set. Okay, to plot it, usually it helps a lot if we put our asymptotes on first. So y equals 1, that's a horizontal line across y equals 1. One thing that they didn't ask for, but it's sometimes helpful to find, are your x-intercepts. So those are the values that make f of x 0, and you can see that's plus or minus root 3. So it's just over 1, so I'm just going to plug them in here, root 3 and negative root 3. I can label those, but we don't have to. Then our other points, we had a local minimum at 0, negative 1/2. Actually, I'm going to move that down a bit. I'll call that negative 1/2. And we've got points of inflection at negative root 2, negative 1/8. So put that right here, and positive 2. So positive root 2, sorry. Root 2 and negative root 2. And this is negative 1/8. Any other main points that we missed? Not really. We know this function is, we know it is even, so it should reflect upon the y-axis, which it does. We know it was concave up in the middle. So that should make sense here, something like that. And then it changes inflection point and it's concave down, but increasing the rest of the way there. Same thing here, concave down, but decreasing as we read left to right. So it should look something like that. Try and over-exaggerate your inflection points like I have here. It just makes the, I guess we could label this negative 1/2. It makes it very easy for the grader to tell you actually know what you're talking about. And that's the function f of x. Not too much else to worry about there. I think this is a fairly straightforward function that goes through all of the normal processes, and we should be able to crush this. On to number 2 here, and it's a classic related rate question. We should see this anytime that there is time referenced in the question. So we have a 40 kilometer per hour speed here, so it's likely going to be related rate because there are things that are changing with respect to time. So let's read it. Eiffel Tower is standing in Paris, 300 meters high, and it's one thing that's not as clear here until it says shadow, but I'll fill that in for you. It says like a light on top, and it's shining down, and there's a car, a double-decker bus that's 4.5 meters high. So the light is causing a shadow of the bus. I'm going to complete the triangle. As we know, a lot of the times this is a related rate question. We want to make a good diagram like this, and this is right angle triangles. So it says, how fast is the tip of the bus's shadow moving when it is 250 meters from the tower? So in other words, this is the shadow, tip of the shadow here, so how fast is this side increasing is basically what's being asked. So I'm going to label that y, let's call it, and I'm going to label this x, primarily because it is helpful to label things that we know we're going to need to find, especially as they're changing. So both x, he's driving away from the tower, so x is clearly changing, as is y. As he gets further out, his shadow is going to change, right? So anything that's changing, try and label that with a diagram, or label that with a variable, I should say. And now we can just see these are similar triangles. So the big to the small to the big, the heights are 4.5 to a ratio of 300. And that has to be equal at all times to the x over y. Seems fair enough. What are we looking for? We're looking for dy by dt. How fast is that length changing with respect to time? I'm just going to cross multiply, and we get 4.5y equals 300x. Perfect. Now in related rate questions, we can just differentiate both sides. We differentiate each variable with respect to time. So the derivative of y is just 1 times dy by dt, and 300x is 300 dx by dt. We were told that dx by dt, or the speed at which he's driving, is 40 kilometers per hour. Perfect. Sub that in and solve for dy by dt. dy by dt equals 300 times 40 over 4.5. dy by dt equals 2666.66. That seems like a fairly high number considering we're driving at 40 kilometers an hour. So what's wrong? Oh, that's exactly it. 40 kilometers per hour. That's no good. We actually need that in meters. So we'd actually times by 1,000 to get it to meters, but then divide back by 1,000 to get it kilometers per hour. So it is kilometers per hour. Seems like a high number, but it's not that crazy given what a small percentage this 4.5 is out of the height of 300. So we know that x is actually, x being the 40 kilometers an hour that it's driving, is a really small percentage of the overall change in speed for y. So that's why it's so large compared to the 40 kilometer hour drive that we're doing. But again, the method for related rates, find a function, find an equation setting up the variables. There can be a million variables in the equation. It doesn't matter because we're differentiating with respect to time. Okay, for number 3, it's pretty straightforward. A good derivative question. We know it's a derivative question because it says tangent lines and their slopes. Slope of the tangent line is another word for derivative. So I'm going to go ahead and find the derivative, even though it seems like we don't have much to offer. Ax squared, the derivative of that will be 2ax, plus b is the derivative of bx. The derivative of c is just a constant, so it'll be 0. So this is our derivative, so I can now use my information that y prime at -2 is negative 4, and y prime at 6 is 28. That's what it means when it says at x equals -2, the slope of the tangent is -4. So I'm just going to set those up, and then we should have two equations, two unknowns. So I'm going to say -4 equals 2a times -2 plus b. And my second equation is 28 must equal 2a times 6 plus b. Perfect. Now I'm just going to isolate b in this first equation, so I get -4 plus 4a equals b, and I'm going to sub that in for b into the second equation. So I get 28 equals 12a plus, subbing in for b is -4 plus 4a. So I get 28 equals 12a minus 4 plus 4a. 16a equals 32. So a must equal 32 over 16 is 2. My a is 2. Sub this back in here and I get b equals -4 plus 4 times 2 for a. And so b equals 4. Perfect. I've got a and I've got b. Still need c, and you'll notice we haven't used our -1,7. That's got to be on this curve. So I'm going to plug in -1 for x, plug in 7 for y, plug in my a and b, and solve for c. So I'll just start here, ax squared plus bx plus c. And I'm going to say 7 equals a is 2, x is -1 at this point, squared, plus b is 4, -1 plus c. And we get 7 equals 2 minus 4 plus c. So 9 equals c. So our parabola is y equals 2x squared plus 4x plus 9. Hopefully that was fairly straightforward. Again, good opportunity for noticing two equations, two unknowns by the fact that we had two different tangent lines given to us. Okay, this one makes sure we actually understand limits. It says show limits to show that this, use limits to show that this function has no vertical asymptotes. Let's think about vertical asymptotes. Those are found when the denominator goes to 0 or has a factor that can equal 0. At that x value, that's where the vertical asymptote is. However, we should know that if we can actually solve for the limit at that point, then it's not an asymptote, but it's a hole or a discontinuity at that x value, because the definition of an asymptote is that our function goes to positive infinity or negative infinity. Let me show you what I mean. As we first look at this function, we should see that the bottom is x minus 1 times x plus 1. So right off the bat, we're thinking that 1 and -1 are not in the domain, which is true. But the question is, are they vertical asymptotes at that point? To test, let's test as the limit approaches these values. 1 of f of x, which is 3x cubed plus 4x squared minus 3x minus 4 over I'm just going to leave this factored, x minus 1, x plus 1. Again, if there's no way we can get rid of this factor here, which is the one that's going to 0 when we plug in 1, then there must be a vertical asymptote there because the whole function would be going to infinity. However, we should be able to factor the top, and the top does factor into x minus 1, x plus 1, and 3x plus 4. You can use any method you like to figure that out. I use long division, and if needed, just send us a note, and we can always point you to a long division of polynomials function. But this is how that top one factors. So what we can actually see is that the two problems, x plus 1 if we are taking x to negative 1, and x minus 1, those can cancel with each other. So the limit actually exists. It exists at plug in 1, 3 times 1 plus 4, which is 7. So the limit as x approaches 1, and the limit as x approaches negative 1 of f of x, that will be 3 times negative 1 plus 4, which is 1. These both exist. Because the limits exist, and they're not going to infinity or negative infinity, then there is no vertical asymptote at 1 or negative 1. In fact, there would be a hole in the function. Okay, to determine absolute min and max, we have to test critical points and test the endpoints of our closed interval, -5 and 2, and just figure out what the highest y value is and what the lowest y value is. Those are the absolute min and max over a closed interval. So I'm going to first find my critical points by setting my first derivative equal to 0. The first derivative of this is going to require a product rule, so it's the derivative of the first 2x times the second, as is, plus the derivative of the second, which is going to be 1/2 e to the x over 2 times x squared, which is the first. Easiest to set this to 0 if we can simplify it all, so I'm going to factor out an x and an e to the x over 2, and I'll be left with 2 plus x over 2. Where can this be 0? Well, this guy can never be 0. It's an exponential function, but it's multiplied by x, so when x equals 0, that's certainly a critical point. And then what would make this bracket 0? Well, if you can't see it right away, just set the bracket to 0. And we get x over 2 equals -2, so x equals -4. These are my two critical numbers. Those, along with -5 and 2, my endpoints, I'm going to just test and figure out what's the absolute min and absolute max. So I'll start from the bottom. I'll do -5, I'll do -4, I'll test 0, and I'll test 2. And what do we get here? We get, I'm plugging this back into the original, -5 squared e to the -5 over 2, which equals 25 e to the -2.5. which is about 2.05 approximately. This would be the same thing, -4 squared e to the -4 over 2, which is 16 e to the -2, which is 2.17 approximately, 2.17. F of 0 should be easy. That's just going to be 0 when you plug it in. And f of 2 will be 2 squared e to the 2 over 2, or just e. So it's 4e, which is 10.87. Therefore, our absolute minimum is found at 0. So at 0, 0, abs min, that's the smallest, and our absolute max is at 2 and 10.87. Or if you want to leave it perfect, it would be 4e. This is the absolute max. So again, find the first derivative, find where it equals 0. Those are your critical points. Test those as well as your endpoints and see what's highest and lowest. Okay, easy derivatives that we're guaranteed to get on our exam. Just whip through each term. When they're added together, a ln function, we take 1 over whatever's inside times the derivative of whatever's inside, which is 6x. Plus, for logarithms, you do 1 over ln of the base, so ln of 3, and whatever's under 1 over whatever's inside. So 1 over x squared is just x squared on top. And minus 6 don't get caught in there. That is just a constant, so nothing there. For part B. Remember, we don't have to simplify either. Do not simplify because we can only lose marks by making extra mistakes. For cosecant, first of all, this 2 on the bottom, I'm just going to ignore that and bring a half out front, and then I'm just going to do the derivative of cosecant. Anything cosecant, we have a chain rule here, is negative cosecant cotangent. So we actually, negative cosecant of the angle, which is cot x over sine squared x, times cotangent of the same angle, cotangent x over sine squared x. This is why this is tricky, because the angle has trig within it. Then you multiply that. I'm going to make a little bit more room, so I'm multiplying all of this in this giant bracket. Multiply that by the derivative of what's inside. And what's inside is a quotient rule. The derivative of the top is cotangent x, so that's negative. The derivative of that is negative cosecant squared x times the bottom of sine squared x minus the derivative of the bottom, which is the derivative of sine squared x is 2 sine x cos x times the top, cot x. And that's all over the bottom squared, which is sine to the 4th x. So pretty tricky there. A quotient rule of trig functions within, and I just want to take that one aside and show you that the derivative of sine squared x, first of all, you want to think of this as sine x all squared, and that's why the derivative is the 2 comes down, then you leave to the sine x to the power of 1 times the derivative of what's inside, which is cos x. And that's how I got that part right here, the derivative of the bottom times the top. Hopefully that helps. Last one's easy. F prime of x is just a product rule. We're going to do e to the 3x. Anytime you have an exponential, you multiply by the derivative of the exponent times the second, so 2 to the x over 3, plus the derivative of the second, which is, you rewrite the exponent, 2 to the x over 3, times ln of 2, the base, times the derivative of the exponent, which is 1/3, times the first to end out the product rule. Okay, here we have an optimization or min-max problem for number 7. I just want to clear a couple things up. So this is a square base container. So square base, and then the height, it'll end up being a rectangular prism. And so the question is, what sort of dimensions do we make? Not the greatest drawing, but good enough. What sort of dimensions do we give it so that we minimize the material used? So we always, for optimizations, want to figure out what we want to optimize. And what we want to optimize is the area. So the area total is the area of the 4 sides plus the base. So I'm going to label the base, it's square, so I'm going to label it x by x, and then the height. So the total area of the entire box will be x squared for the base plus 4 xh. X times h is the area of one side, and there's 4 of those sides. Step 2 is to use another piece of information to be able to get this equation in terms of one variable. Right now it's in terms of x and h. We can't derive it until we have it in terms of one variable. So we're going to use the fact that 36,000 must be the volume, which is x squared, the area of the base, times the height. So I can use this to isolate for h, which will be 36,000 over x squared. Perfect. Now I can sub this in for h here and then derive the area function because that's what I want to optimize. So the area function now equals x squared plus 4x times 36,000 over x squared. Once I've subbed that in for h, one of our x's will cancel, and we've got a equals x squared plus 4 times 36,000 is 144,000 over x. Now the next step is to differentiate my function. I'll call it a prime of x equals 2x minus 144,000 over x squared. I got that because I know the derivative of 1 over x is negative 1 over x squared. You can always test that out by doing the exponent law, where you call that x on the bottom is x to the negative 1 on top. Now I'm going to set my derivative equal to 0 because I want to find the spot that will maximize it. 144,000 over x squared. And we get 144,000 over x squared, equals 2x, cross multiply, and we get 144,000 equals 2x cubed, 72,000 when we divide by 2 equals x cubed, so x equals the cubed root of 72,000, which is about 41.6 centimeters. 6 centimeters. So that should be the length of the base. And you can plug that back in here for h, and you'll get h equals 20.8 centimeters, which coincidentally happens to be half of the base length for the height. So the majority of the area is found on the base, and then each face is a little bit smaller. Hopefully that's helpful. Again, going through those steps for optimization. Get a formula for the thing that you want to optimize, area in this case. Use the other piece of information to substitute out and get that formula in terms of one variable. Differentiate, set equal to 0, and solve for x. Then you always want to go back to the question and determine what they asked for, and in this question they asked for the dimensions, so we found x and h. Okay, for the theorem questions, part A says show using the extreme value theorem that this function has a minimum value on the interval negative 2, 2, but it doesn't on negative 4, 4. And this is really simple. It's because the extreme value theorem says that the function has to be continuous on the closed interval. And if that is the case, then within that interval there must be a minimum value and there must be a maximum value. Since the function is continuous from negative 2, 2, that's perfectly acceptable. There must be a minimum value somewhere in that interval. But from negative 4 to 4, that crosses over x equals 3, and we can see that x equals 3 is not in the domain, because that will make the denominator 0. So that's why there's a minimum. There must be a minimum value on this interval, but not on this one, according to the extreme value theorem. For Rolle's theorem, we're given an interval of negative 1 to 1, and it says show the function will have a critical value, and because f of negative 1 equals negative 1 squared minus 1 over negative 1 minus 3 equals 0, and f of 1 also equals 0, just by plugging that in, we know that endpoints having the same y value essentially states that if it's differentiable across that interval, then there must be a critical value, or a stationary point, it truly says, between those two endpoints. So because we've shown that, for instance, some function at 1 it's 0 and at negative 1 it's 0, then there must be, if it's going to go from here to here, if it gets back to that same y value, there must be a stationary point at some point between those two functions, at least one. Okay, for number 9, this is the classic antiderivative question. Every time we go up a level, we have to add the plus c, or the constant. So that's exactly what we've got here. We've got h double prime, we've got h prime, and we've got h of 1. So we actually know something about h of x, but we've got to find the whole function h of x. So I'm going to start at the second derivative, and I'm going to take the antiderivative. So I'm going to say h prime of x must equal 2x, because that's where 2 came from. We're at minus x to the negative 2, so we must have been at plus 1 over x, since the derivative of 1 over x is negative 1 over x squared, plus c. Now I can use the information I have, which is h of 1 equals 6, or h prime of 1 equals 6, sorry. So I'm going to plug in 6 equals 2 times 1 plus 1 over 1 plus c. So 6 equals 2 plus 1 plus c, therefore c must equal 3. And I can now update this function to h prime of x equals 2x plus 1 over x plus 3. Now I can go one more level up to find h of x. If I have 2x, I must have come from x squared. If I have 1 over x, I must have come from ln of x. If I have 3, I must have come from 3x plus d. There could be a constant there. Now I can use this piece of information that when x is 1, h of x is 8. So I'm just going to sub in 8 and 1 for x, plus ln of 1 plus 3 times 1 plus d. 8 equals 1 plus 0. Ln of 1 is 0 plus 3 plus d. So d must equal 4. So my final function h of x is x squared plus ln of x plus 3x plus, instead of d, I can now write 4. Textbook question, start at your highest derivative and take your antiderivatives back to start filling in your constants. Okay, on to integrals for number 10. First thing to note is this is an indefinite integral. There are no limits here, so we don't need to worry about plugging in values at the end. We've just literally got to take the antiderivative. It's a quotient, so as far as we know in this course, we need to be able to simplify so that we're in sort of polynomial form, or at least in multiple terms, added or subtracted. X to the 1/2 on the bottom is the same as root x. So as we simplify and we divide this into each term, divide it into there, divide it into there, and divide it into there, each term is going to get a little bit simpler. 3 root x over root x is just 3 e to the x minus secant squared x, because the roots cancel there, plus, here we actually have to do a subtraction, so it's going to be x to the 4 minus 1/2, because we subtract exponents when we divide terms. So 4 is like 8 over 2 minus 1 over 2 is 7 over 2 dx. Now we have 3 easy terms that we're very good at anti-deriving. So we just take the antiderivative of each. 3e to the x couldn't be easier. It's still 3e to the x minus, if we're at secant squared of x, that's the derivative of tan x, so we must have come from tan x, plus, here we go up a power, so we're at 7 over 2, up a power by 1 is 9 over 2, divided by 9 over 2, which is the same thing as multiplying by 2 over 9. Don't forget your plus c, and you're done. Again, just to show again how I did that last term, x to the 7 over 2. 7 over 2 plus 1, I must have come from 1 power higher. So that's 7 over 2 plus 2 over 2, which is the 9 over 2. And then dividing by a fraction is like multiplying by the inverse, or the reciprocal, I should say, 2 over 9. Okay, last question on the exam is to find the area bounded by, I added in something here that wasn't in the print. I put the negative x-axis, the y-axis, and the function. So this will make a little bit more sense. This function, if we don't know what it looks like, I would recommend a table of values. However, we should know this is a parabola with vertex at -1, -1, and 9, and it's facing downwards. Now we want to find the x-intercepts because it's bounded by the x-axis as well. So I'm just going to plug in 0 for y, negative x plus 1 squared plus 9, x plus 1 squared equals 9, so I'm going to take the square root of both sides. I get x plus 1 equals plus or minus 3. So x plus 1 equals 3 and x plus 1 equals minus 3. So x equals 2 or x equals negative 4. So those are going to be the sites of the x-intercepts. And the function looks like this. Okay, so we want the area between the negative x-axis I added in and the y-axis, as well as the function. Otherwise, it doesn't really make sense because you wouldn't even need to say the y-axis because it would include this piece too. So I like adding the negative x-axis. Now, the reason we need to both draw and solve for those values so that we're accurate is because we need to actually calculate this area. So we need the x value boundaries. Clearly it's below the curve, so I just want to take the integral of the curve from my boundaries. X equals negative 4 to this point here, which is where x equals 0. So I want to go from negative 4 is my lower limit to x equals 0 of the function negative x plus 1 squared plus 9 dx. I want to integrate with respect to x. We can either multiply this out if we want a polynomial, or we can just, there's no chain rule needed because x is just to the power of 1. However, I will multiply it out just so that we're clear. So this is the integral of negative 4, negative, it'll be x squared plus 2x, so negative 2x. You'll get plus 1 when you multiply the brackets out, and negative 1 plus 9 dx, which equals negative 4, 0, negative x squared minus 2x plus 8 dx. Now it's time to actually find the antiderivative of each and then solve. X squared must have come from negative x cubed over 3. Negative 2x must have come from negative x squared. 8 must have come from 8x. This is a definite integral, so no need for the plus c. We're going to evaluate from negative 4 to 0. When we plug in 0, we get 0, so that one's easy. Then it'll be minus, plug in negative 4. And we get 64 over 3 minus 16 minus 32. And when we run the negative through, we get 26.66 units squared. So again, we're just doing antiderivative of all of these to get that expression there. Then you plug in the top limit, minus plug in the bottom limit, and that's your total area that we found. Find the x boundaries, take the top function minus the bottom function, which was just the x-axis, so we didn't need to worry about that, and then solve the integral. Hopefully that was helpful. You can always download our app, our iOS app, AT Now. Really helpful for last-minute questions, as our tutors are on there every weeknight. And you can always send us more questions to info@arnoldtutoring.com, or check out our YouTube channel. Thank you again for coming to the seminar, and I hope you found this helpful.